Okay, so types of mechanical energy. We've got kinetic energy versus potential energy. And what's the difference between those? What distinguishes kinetic energy specifically?
Speed?
Yeah, kinetic energy relates to speed, the idea that the object is moving. And there's really two types of motion. An object could be translationally moving. Translational motion means it's just moving through space. It's changing its position as time passes. But other than just moving through space, how else could an object be moving other than changing its position as time passes?
Direction?
It could be changing. What do you mean by direction there?
I mean, like an object could be moving up, down, left, right, something like that, right?
That all still counts as translational motion, though. If it's moving forward or backward, or left or right, or up or down, those are all changing its position as time passes. And we define that in terms of how quickly its position is changing. So translational motion means the position is changing. And we define the velocity, translational velocity, as v equals derivative of position with respect to time. How much or how fast the position is changing as time passes. So, and we can also approximate that as just delta x over delta t. Difference being that delta x over delta t is how far you travel divided by how much time it takes. Dx dt, the derivative, is how fast your position is changing at that instant. So exact rate of change at that instant versus average rate of change over a period of time. In the same sense that, for instance, if I travel, let's say, 500 miles in 10 hours, 500 miles divided by 10 hours is 50 miles per hour. But that doesn't mean I'm traveling at 50 miles per hour the whole time. My instantaneous rate of change could be changing as time passes. Maybe sometimes I'm traveling faster, sometimes slower. But the average rate of change is total distance traveled over total amount of time passed. But that's all called translational motion. The object is moving through space. It's changing where it is as time passes. What's another way an object could be doing something that still counts as moving, even if it's staying still, even if it's staying in place?
Change in distance?
That's still traveling, though. You could have rotational, though, yeah. If an object is staying in the same place, but it's spinning around, that still counts as a form of motion. That would be rotational motion. Rotational motion means the orientation is changing. It's changing which direction it's facing. So these both count as forms of motion. For rotational, though, we're not looking at how fast the position is changing. We're looking at how fast the orientation is changing, how fast it's spinning. And the rotational velocity, usually written as the Greek letter omega, if an object is spinning, so it's not moving through space, it's just spinning where it is, what's changing as time passes? How would you describe how fast it's rotating, how much it has rotated? Like numerically, how could you distinguish between an object that's rotating very slowly versus an object that's rotating very quickly? How would you describe numerically how fast something rotates?
The angles, like angles per time.
Angle over time. Yeah. So we can treat rotational velocity, usually written as the Greek letter omega. We define that as change in angle, usually written as theta, over a change in time. So how much the angle changes divided by how much time it takes. So for instance, if you complete one full rotation, over the course of 10 seconds, your angular velocity would be 2 pi, because one full rotation in radians is 2 pi. 2 pi divided by 10 seconds. So that'd be 2 pi over 10, which reduces to, so 2 pi radians over 10 seconds reduces to pi over 5 radians per second. So that would be the angular velocity. Any questions on that so far? And of course, you could have both. If you have like an object that's spinning as it moves, or if you've got maybe a wheel rolling on a surface, it's changing its position as time passes and it's changing its orientation as time passes. So it's entirely possible for an object to be translationally moving and rotationally moving at the same time. Wheel rolling on a surface, or an asteroid tumbling through space, rotating as it moves. It's entirely possible to be doing both at the same time. Any questions on that distinction so far? And those both have kinetic energies associated with them. If an object is moving through space, if its position is changing as time passes, it has a property called kinetic energy, specifically translational kinetic energy. Translational kinetic energy, which is usually just what we're talking about when we say kinetic energy, is the energy associated with translational motion, moving through space. So if an object is changing its position as time passes, it has translational kinetic energy. There's also rotational kinetic energy. If an object is spinning, it has energy associated with that spin, and that's called rotational kinetic energy. And usually if you just see kinetic energy without a label, that usually means translational kinetic energy. If both are involved, though, it's important to label which is which. And do you have a formula for translational kinetic energy yet? What should that depend on? What would you expect to be the indicator for translational kinetic energy?
Would it be half mv squared?
Because it's going to involve velocity. I mean, the very fact that it's the energy of motion means velocity has to be involved somehow. And mass is also going to be involved in the sense that if you think of kinetic energy as how much work it takes to get something moving that fast in the first place, more massive means it's going to take more work to get it moving at a certain speed. And to get the units to work out right, you also need a squared here. It turns out there also is a 1/2. And the reason for that actually has to do with calculus. Have you seen any concepts in calculus where you end up with a variable being squared and multiplied by 1/2? Is there any operation you could do that results in something like x squared with a 1/2 multiplier?
Taking the integral?
Yeah, specifically the integral of what?
Of x?
Yeah, this is just the integral of x itself. Integral of x specifically to the first power, though we usually don't bother writing out the first power. You add 1 to the exponent, divide by the new exponent, you get the antiderivative. It turns out that this is also from an antiderivative, specifically the antiderivative of mv with respect to velocity. This mv quantity is called momentum, and we're going to look into that in more detail in 7b. But this kinetic energy is calculated in the first place by taking the integral of mass times velocity with respect to velocity. In fact, anytime you see a quantity that's defined as something like a variable to a power divided by that power, that usually is because it comes from an integral in the first place. The formula originated from an integral. Any questions on that so far? So that's our formula for kinetic energy. And let's take a look at the units of that as well. What are the usual units for mass?
Kilograms.
Yeah, we measure mass in kilograms. And velocity would be measured in what?
Meters per second.
Meters per second. If you take a look back at how it's defined, it's a distance over a time. Distance is measured in meters. Time is measured in seconds, so velocity is going to be meters per second. But then we're squaring that, so we get kilograms meters squared per second squared. Kilograms times meters squared over second squared. But we're claiming this is a form of energy, and we already measure energy in what units?
Joules.
Joules. And this is actually how we define joules. Joule means kilogram meter squared over second squared. In fact, many units of measurement are just abbreviations for more complicated clusters of simpler units. Kilograms, meters, and seconds are some of the most fundamental units of measurement there are. They're not defined in terms of other things. A kilogram is just a certain amount of mass. A meter is a certain amount of distance. A second is a certain amount of time. Joule, though, joule is not really a fundamental type of unit. Joule is a combination of several other types of units. Anytime you see joule, it can be replaced by kilogram meter squared over second squared. And in reverse, too. Anytime you see kilogram meter squared over second squared, you can replace it with joules. It's just an abbreviation for that cluster. And every form of energy should be measurable in joules. If it can't be measured in joules, it's not the energy we're talking about in physics. Any questions on that so far? As usual with energy, though, we don't really care how much energy something has. What do we care about in the energy interaction model? Not how much energy it has, but how much what?
Change.
Yeah, how much it changes. So let's take a closer look at the change here. If you want to find the change in energy, how do you calculate change in anything?
Usually like final minus initial.
Yeah, if we just write out the delta as final minus initial, so that can be expanded as this formula twice. So 1/2 times the final mass times the final speed squared minus 1/2 times the initial mass times the initial speed squared. However, what's the only part of this you would expect to be changing from initial to final?
Velocity?
Yeah, we would expect maybe the velocity is changing. Maybe it's traveling at some speed and then it gets faster or it gets slower. The mass we would generally expect not to change. So I'm going to ignore the labels on mass. It's not like you have an initial mass and a final mass. It's just the mass of the object. There are some circumstances where the mass can change. Like if you've got a rocket that's burning fuel, the exhaust from the burned fuel is expelled out the back and is no longer part of the mass of the rocket. Or if you've got, let's say you've got a boat traveling on a lake and it's gradually filling up with water because it's raining. Then the mass of the boat, including the water inside, is going to be gradually increasing. So there are some circumstances where mass could be changing. But I think in the vast majority of circumstances we're going to be looking at, probably all the circumstances we're going to be looking at, we're going to assume the mass is constant. And if this same 1/2 m, 1/2 m shows up in both terms, what can we do algebraically if we've got the same concept in both, same multiplier in both terms?
Cancel it out.
We could only
Take it
cancel it out if we're dividing by 1/2 m, and there's not really anything to divide by because we don't want to divide the other side by 1/2 m.
We can pull it out of the equation and put both of these in parentheses.
If we pull that out, if we factor out the 1/2 m using the distributive property, what's left?
1/2 m times vf final velocity squared minus initial velocity squared.
Yeah. And this now looks like a delta itself. This is change in speed squared because we've got the final value of speed squared minus the initial value of speed squared. And notice that's not just change in speed, that's change in squared speed. So we can abbreviate this as change in kinetic energy, at least the translational version, is 1/2 times m times delta speed squared. And we usually include parentheses around the speed squared because this is just emphasizing that you square both the speeds first. You square the initial speed and square the final speed, and then subtract to find the difference in squared speed. Speed squared is not quite acceleration. Acceleration is defined in terms of speed, though. The way we define that, in the same way that the speed is defined as how quickly the position is changing, acceleration is defined as how quickly the speed is changing. So if you, it's not the speed squared, it's the derivative of speed. It's talking about, acceleration is talking about how fast is the speed changing. And since speed itself is a derivative, that means acceleration is the derivative of position. And what do we call the derivative of a function? If you got a function and you take its derivative and then you take the derivative again, if you've got some function x and you take the derivative and then you take the derivative of that, what notation would we use to combine these together? dd would usually be written as, yeah, x double prime. Either d squared, because you got dd, over dt squared, because we've got dt x, or that might just be written as x double prime. So we could say that velocity is the first derivative of position, acceleration is the derivative of velocity, and therefore the second derivative of position. So this is how those quantities are related to each other. Position, velocity, and acceleration are defined in terms of derivatives, rates of change. Any questions on that so far? And if we take a look at the units, we already know that speed is measured in meters per second. So if we plug that in here, speed is in meters per second, but we're dividing by time, so that introduces another seconds. So we got meters per second divided by seconds, and what units would that become? Yeah, meters per second squared. Because these seconds and seconds are both in the denominator. So that means they're going to combine, and we get meters per second squared. Sometimes that's read as meters per second per second. It's really just telling you how fast the velocity is changing. How many meters per second the velocity changes every second. Any questions on how those are defined so far? All right, so that's translational kinetic energy. And note that if the translational kinetic energy is changing, the object is accelerating. Because the translational kinetic energy only changes if the speed changes. And if the speed changes, that means the object is in the process of accelerating. So there has to be acceleration happening in order for kinetic energy to change. So we're defining translational kinetic energy as 1/2 mv squared. But usually it's more important to know the change in kinetic energy, which is just 1/2 m delta speed squared. In fact, you could just visualize that as applying a delta to the whole thing, but any constant multipliers, anything that's not changing as a multiplier can be pulled out of the delta. And that really is just factoring. Any questions on the translational kinetic energy so far?
So you said that there has to be acceleration to have a change in kinetic energy, right?
Yeah, in the sense that the kinetic energy only changes if the speed is changing.
Yeah.
And the change in speed, or rather the rate of change in speed, is called acceleration.
Acceleration. Okay, so like when a problem says an object is moving at a constant speed, that could be indicating that there might not be kinetic energy change.
Right. If an object is moving at constant speed, then it has kinetic energy, but the kinetic energy is not changing. So delta KE.
Yeah.
And in fact, even if it is changing speed, If it starts at a certain speed and ends at that same speed, like maybe it gets faster and then gets slower again, if it starts and ends at the same speed, what's delta kinetic energy going to be?
It's not going to change.
Right. Even though there's changes in between, initial and final values being the same means the total change is 0. And this is very convenient for energy interaction diagrams. If you can choose an initial and final time that have the same speed, then you know that overall the kinetic energy is not changing. And therefore you can just leave kinetic energy out of the diagram entirely, if all you care about is initial and final values. The rotational kinetic energy is going to use a similar structure, but different variables. Specifically, it's going to depend on omega, the angular speed, how fast the angle changes as time passes. Omega squared. It's also going to have a 1/2, again, because of the squared, and it's defined in terms of an integral. But it turns out that just mass alone doesn't work here, because the units of this are radians per second instead of meters per second. So if you just take omega squared and multiply by mass, you get kilograms, you get seconds squared, you get radians squared, but you're missing meters squared. So it turns out this needs something that's not just mass, but something called moment of inertia. Moment of inertia is basically a measure of how difficult it is to rotate an object. Like if you've got a really lightweight wheel that's easy to spin, that's got a very small moment of inertia. If you attach some extra mass to it so it's more difficult to spin, that's a larger moment of inertia. And also if you take that mass and move it further towards the outside, even if it's the same amount of mass being further out, like if you've got extra weights glued to the rim of a bicycle wheel instead of glued to the inside, extra weights out on the edge are going to make it even more difficult to rotationally change. So moment of inertia ends up depending not only on mass, but also how far the mass is from the axle. We're not going to look at moment of inertia in a lot of detail until we get to 7b. In 7b, we're going to do a lot more with rotational stuff. For 7a, though, just keep in mind that an object that's spinning has rotational kinetic energy. And if you wanted to get it to spin in the first place, you've got to do work to it to give it kinetic energy rotationally. If you want it to stop spinning, you have to remove energy so it loses its rotational kinetic energy. Any questions on that so far? So that, I think, is everything we're going to need for kinetic energy. It's just the energy of motion. Could be having energy because it's moving through space, or could have energy because it's rotating, or could have both. Let's take a look at the potential energies. And potential energy is a much more broad general term. Potential energy is basically any energy associated with position or orientation or even shape relative to other objects. And you could think of potential energy as energy that is being stored, energy that is stored in some way that could later be used to do work. Like let's say you've just got an object. Is there any way you could do work to this object in a way that is storing it up for later? First of all, what has to be happening to count as doing work? To count as doing work, you've got to be applying, you've got to apply a force. And like I'm applying a force to this eraser right now just to hold it in place. I'm acting against gravity. Gravity is pulling it down. My hand is holding it up. So I am applying a force. Does that count as doing work? Am I investing energy into this just by holding it here?
Yes.
So is it gaining energy right now? As we speak, is it gaining more and more energy?
No.
So that means I'm not really doing work. Because work is a transfer of energy. If you're doing work to something, you're either giving it more energy or taking away some of the energy it already has. I'm not investing more energy into this just by holding it here. I'm applying a force, but it doesn't count as work because what is it not doing?
There's no displacement.
Yeah, there's no displacement. There's no motion. in order to count as work, you have to be applying a force to an object as it moves. So for instance, if I lift the object, I'm applying an upward force to cancel out gravity, and also the object is moving upwards. Since I'm applying a force to an object that is moving in that direction, that means I'm doing work. Work is the combination of force and distance. Force times distance traveled. And this might be delta X or delta Y or whatever, depending on direction. But it's just the amount of force you're applying times the distance traveled. And they have to be at least partly in the same direction. If they're perpendicular, like for instance, if I'm holding this eraser, I'm applying an upward force just to counteract gravity. So I'm applying an upward force. If it's moving sideways, my force and the motion are perpendicular, so that doesn't actually count as work. My force isn't really influencing the motion. But if I'm moving it upwards, I'm applying an upward force as it moves upwards, so I'm doing work. Or if I move it downwards, I'm applying an upward force while it moves downwards. That actually means I'm doing a negative amount of work. I am removing energy from it. The thing is though, if I take some heavy object and I lift it up, I'm doing a lot of work to lift it up because I'm applying a lot of force. If I then put it on a shelf, I've stored that energy. The object now has potential energy because I've done work and I've stored it by leaving it there. How could I get that energy back? If you got a heavy object on a tall shelf, you've invested a lot of energy. How do you get that energy back?
Let it fall?
Yeah, if you knock it off the shelf and let it fall, it loses that energy you've invested. And also as it falls, it gets faster and faster, which means it's gaining what type of energy?
Kinetic.
Kinetic, exactly. By lifting the object, you're doing work to give it potential energy. So it now has lots of potential energy. If you let it fall, it loses potential energy and gains kinetic energy. So that's really the sort of transfer we're often talking about. While it's being lifted, first of all, while it's being lifted, would it be a closed system or an open system? If I'm lifting this object up, would that be an open system or a closed system?
A closed system.
And
Would it be open because it's reacting to external factors, which is like if it's just the eraser, it would be an open system because it's your hand, which is an external factor that's influencing it being lifted.
Yeah, exactly. While I'm in the process of lifting it, my hand is doing work to the eraser. If the system is the eraser, then I'm doing work to the eraser, and that counts as an external work, external transfer. So while I'm lifting the object, the potential energy is increasing. It's gaining energy related to position. And specifically, what type of energy would we call that? What force am I acting against when I'm lifting the eraser?
Gravity.
Gravitational.
I'm acting against the force of gravity, so we call this gravitational potential energy. Potential energies are usually defined in terms of some force. This is called the gravitational potential energy because you have to do work against the force of gravity in order to create it, in order to invest energy into this. And what's the indicator for that?
Is it the height?
Right. The height is increasing. That's how we know it's gravitational potential energy. So we say its Y value, its height is increasing. And we're treating this as an open system because the person holding it is doing work entering the system to cause the potential energy to increase. So we lift it up, we're doing work, increasing its potential energy, we put it on the shelf, that energy is now stored. This is a very good way of thinking of potential energy, energy that has been presumably or possibly created by work. We don't really care where it came from, but maybe created by doing work to the object. And then the energy is now stored in the object or stored in the position or orientation. It's really about storing energy in an arrangement of objects because it's not really just the eraser. Potential energy of gravity is about the relationship between the eraser and what else? Why do we have gravity in the first place here? It's the gravitational
eraser and the Earth.
Magnitude of the Earth.
Exactly, the Earth itself. That the eraser is interacting with the Earth. The Earth has a huge amount of mass. The eraser has a little bit of mass. Objects with mass pull on each other. So the Earth is pulling the eraser down. The eraser is also pulling the Earth up, but we don't really notice that because the Earth is so massive. But the system we're talking about here is really the combination of the eraser and the Earth. So this would be the eraser-Earth system. Technically, anytime you're including potential energy of gravity in a system, you're including not only the object, but also the planet it's on. Those are both considered part of the system. When do you not include Earth in the physical system? You kind of have to in this case, because without the Earth, there wouldn't really be an arrangement of objects. Potential energy is usually about a relationship between objects or collections of objects. So potential energy of gravity is always about a relationship between two objects with mass, in this case, the eraser and the Earth. We're only really considering the motion of the eraser. We're not treating the Earth as moving here. But the gravitational force is between those two objects. So you do need to include both of them when you're describing the physical system. What else? Also, when it's falling, if you just knock the object off the shelf and it starts to fall, then what types of energy are changing?
Kinetic energy.
Yeah, we've got kinetic energy because the object is now moving and it's changing how fast it's moving. When we're lifting it, we're just assuming it's being lifted at a constant slow speed, no changes. But when it's falling slowly, then faster, then faster, then faster. So kinetic energy would be increasing. And would you consider that rotational or translational kinetic energy?
Translational?
Yeah, definitely translational kinetic energy because it is changing its position. It's moving through space. And more importantly, it's changing how fast it's moving through space. So for the indicator for that, we're going to use speed. But we usually rate that speed in absolute value bars because positive and negative can make a difference here. What would you expect positive or negative to represent for speed?
Direction?
Yeah, we usually use positive and negative to represent direction of travel. For vertical, we usually define upwards as positive and downwards as negative. You don't have to. You could say downwards is positive and upwards is negative, as long as you're consistent about it. But it's usually easier to make sense of what's going on if you treat upwards as the positive direction. However, what's being done to V in the equation for kinetic energy? If you go back to your equation for kinetic energy, V is being
squared.
It's being squared. And what happens to a positive or negative number when you square it?
It loses its sign if it's negative.
Exactly. It loses its sign. Positive stay positive, negative stays positive. So sign doesn't really matter. And for that reason, we usually write the indicator as absolute value of speed. We don't care which direction it's moving. We just care about, is it getting faster or slower? As the object falls, it's got a negative velocity that's getting more and more and more negative. Technically, if a number is negative and getting more negative, is that an increase or a decrease?
That's a decrease.
Yeah, that is technically a decrease. Negative 10, for instance, is less than negative 3. So if the object's velocity is negative and getting more and more negative, that is technically a decrease. But we don't want to say that kinetic energy is decreasing. So we use absolute value as the indicator. Absolute value of negative 10 is going to be 10, which is greater than absolute value of negative 3. So as it falls, it's getting faster and faster, which means the absolute value of speed is increasing, meaning the kinetic energy is also increasing. But what else is changing? Lifting the object, eraser Earth system. The idea is that the physical system we're describing here is not just the eraser, it's the eraser and the Earth. Because the potential energy of gravity is really a description of how the Earth and the eraser are interacting with each other. You can't have potential energy of gravity with just one object. And potential energy should also be changing too, changing here, right? We've got potential energy of gravity because the height is, as it's falling, height is decreasing. And therefore potential energy of gravity is also decreasing. Are there any other types of energy that could be changing as the object falls?
Thermal energy?
We might possibly have thermal energy. Maybe the object is getting warmer. And what could cause that? What could cause an object to get warmer as it falls?
Friction.
Yeah, friction with, specifically friction with what? What else is it interacting with as it falls?
Air.
Right, it's interacting with the air. So we might have thermal energy, possibly just thermal energy of the object, possibly thermal energy of the air, possibly both, increasing as those temperature or temperatures rise. As long as we include that, this would count as a closed system. If you didn't include thermal energy, we'd have to treat this as an open system because energy would be leaving the system for something we're not including. But as long as you're including everything that's changing, this does count as a closed system. So presumably we're going to get a large decrease in potential energy, an almost as large increase in kinetic energy, and maybe a small increase in thermal energy. However, if we're assuming that the air resistance is very small, we can usually ignore this increase in thermal energy and still treat it as a closed system. Because the amount of air resistance, the amount that the air is pushing back, what would you expect that to depend on? What determines how strong the force of air resistance is? Like for instance, if you hold your hand out the window of a moving vehicle, you feel the air pushing on your hand. What's going to determine how hard the air is pushing on your hand?
The speed at which the car is moving.
Right. The faster you're moving, the harder the air is pushing on your hand. So the amount of energy you lose to air resistance depends, at least in part, on your speed. If you're traveling at a very fast speed, you're going to have a lot of thermal energy change, a lot of energy lost to air resistance. If you're traveling at slower speeds, it's not going to matter as much. And what counts as slow speeds versus fast speeds largely depends on the object itself. If you've got a very massive compact object like a rock, that's going to be able to travel pretty fast before air resistance starts to play a major role. But if you've got a large and lightweight object like a piece of paper or a feather or a styrofoam ball, then air resistance is going to play a very major role. So generally for small compact objects, we can often ignore the air resistance component and just treat kinetic energy and potential energy as a closed system. But either way, this explains why the object is getting faster as it falls downwards. It's losing potential energy because of the downwards motion and gaining kinetic energy because it's speeding up. Those changes, if we ignore air resistance, should balance each other out. Any questions on that so far?
So for systems, so is the determining factor for like whether there's thermal energy or not is the weight? Because like let's say there's like a golf ball falling and like a coffee filter falling. Mm-hmm. Like I feel like the air resistance would be negligible in one scenario but not in the other. So like is there like a specific factor that determines whether there's thermal energy or not?
It's really a combination of, well, partly it's related to how fast it's going. Any object is going to experience basically no air resistance if it's going very, very slowly. Any object is going to experience lots of air resistance if it's going fast enough. But the breaking point between probably negligible and probably should be included really depends on the object. Like as you said, with the golf ball versus the coffee filter, the golf ball can be falling pretty fast before air resistance becomes a major role. Whereas the coffee filter, you drop it and it just floats slowly because air resistance becomes important almost immediately. What's really the difference between those two objects that makes the difference there?
Surface area?
Surface area is part of it. Or not so much surface area, it's more about the cross-sectional area. How much space it takes.
Apart.
What was that?
I was just gonna say like how the mass is spread apart. Like distributed.
Yeah, if it's spread out a lot, specifically spread out in the plane perpendicular to the direction of travel. Like if you've got a piece of paper, as the piece of paper falls, since it's taking up this much surface area or cross-sectional area, as it moves, it has to push all this air out of the way. So the wider it is in terms of cross-sectional area, the more air it has to push out of the way as it moves. So large cross-sectional area suggests that air resistance is going to play a major role. But also, if you had like let's say a block of iron that was this same size, it's going to fall pretty fast. Air resistance won't matter much. Because for that block of iron, even though it's pushing the same amount of air out of the way, what's different about the iron?
It's more like compact, I guess.
It's not more compact. It's the exact same size. If we just take a rectangle of iron that's the same size, 8.5 by 11 inches, and drop it, it's the same size, so we can't say it's more compact.
Would it be the mass?
It's a lot more massive, right? If you've got this block of iron that's the same size as a piece of paper, but it's much more massive. So it actually has the same pushback from the air. If it's the same shape, same size, same shape, same speed, it has the same amount of pushback from the air. But the force of gravity is so strong because of the mass that the air resistance is negligible compared to the force of gravity. So an 8.5 by 11 piece of paper and an 8.5 11 piece of iron, they're going to experience the same air resistance as they move. But for the iron, the force of gravity is so much stronger that the air resistance doesn't really matter in comparison to that. So it's really that the air resistance is negligible compared to the other forces involved. So in this case, force of gravity.
So
what was that?
Oh, so I was just gonna ask if like another way to look at that would be, because it's a bigger object, that objects between Earth has a larger attraction.
Yeah. Although I would be careful about using ambiguous terms like bigger. You want to specify what aspect of it is greater. In this case, more massive, I would say.
Okay.
So more massive, but the same area, same size. So generally for an object that's very massive and doesn't take up much space, you can assume that air resistance is negligible, unless it's going at ludicrously fast speeds. Like for instance, a spaceship crew capsule on its way back to Earth from orbit. It's fairly small, very massive. It's coming screaming in at extremely high speeds though. So at high speeds, even that compact, massive object is going to hit lots of air resistance. But in general, at typical everyday speeds like dropping a rock off a building or something, if the object is very small in terms of volume, but very massive, then you can ignore its air resistance. But if it's much more spread out and low mass, then you would assume that air resistance plays a major role. Any questions on that so far? All right, we are about out of time, but let me give you one practice problem to try out on your own. Let's say you have a rock, let's say a 5 kilogram rock, and you're at the top of a 20-meter tall building. You got a 5 kilogram rock, you're at the top of a 20-meter tall building, you drop the rock, see if you can figure out what speed the rock is going at the instant it's about to hit the ground. So just before it hits the ground, how fast is it moving? Try that out on your own, see if you can put together these ideas of kinetic energy and gravitational. Did we actually get a formula for gravitational potential energy? I think we didn't actually get to that. Have you seen a formula for gravitational potential energy yet?
Yeah, it's mgh.
Yeah. Or I'm going to say m times g times y, because we often use h for another value. But potential energy of gravity, mass times acceleration of gravity times height. See if you can use that and the formula for kinetic energy. Initial, the instant you drop it. Final, the instant it's about to hit the ground. Let's try setting up an energy interaction diagram and figure out how fast is it moving the instant it contacts the ground.
Is there air resistance?
Let's assume no air resistance. Let's assume it's a heavy object that's fairly compact. You just got this rock and you're just dropping it off the building. So ignoring air resistance, using a setup like this, see if you can figure out algebraically how fast is it going to go when it hits the ground. So try that out, and we'll look into some more examples next time.
Thank you.
You're welcome.